Hello everyone. Don't know if many of you have had a chance to go through example number 4 and 5 from yesterday, but they were a bit tricky, so I figured I'd give you some help with those. So first off, I've gotten the derivative done for you there. So derivative is 2 cos x plus 1. We're interested in intervals of increase and decrease. So the boundaries will be when cos x is -1/2. Okay, so looking at our unit circle, that happens here and then there. And if we go full circle again, so beyond, right, continue along to there, it happens again at 8 pi over 3, so there, and then further along still, it would happen again at 10 pi over 3, and so on, right? Okay. So those are our kind of two boundaries in one full circle. So if we set up our areas to look at, cos x plus 1/2, if we start at 0 and we go all the way along here, it's positive up until we reach that point. Okay, and beyond that point, cos x will be less than -1/2. So this thing here will turn out to be negative after 2 pi over 3. Okay, so it's positive from 0 to 2 pi over 3, and then it goes negative, and then so it'll go negative in this region from 2 pi over 3 to 4 pi over 3. And then again, so to the beyond that, cos x is going to be greater than -1/2. So we go positive again on this arc, right? And it'll be positive all the way through until we get to 8 pi over 3. So that'll be positive. And then going from 8 pi to 10 pi over 3, we're looking at this arc. That's going to be negative, okay, and so on. So what that means for, okay, so that's the derivative, right? So slope is positive here, then it goes negative. So if we're going from a positive to a negative slope, there's going to be something interesting happening there. So it's increasing, the function is increasing there, and then it's decreasing. And then it's increasing again, and then it's decreasing. Okay? All right, so we can list intervals in general for when it's increasing, so we can just kind of follow along with the unit circle, right, forever if you wanted to. The intervals where we're increasing for f of x, we could start at, say, so let's go, so -2 pi over 3 to 2 pi over 3. Okay, we're increasing on that interval. Okay, we're also increasing on the interval from 4 pi over 3 to 8 pi over 3. And we're also increasing from 10 pi over 3 to 14 pi over 3, and so on. Okay, so with this, you can kind of craft a general rule for these terms in front. Notice to get from -2 pi over 3 to 4 pi over 3, I need to add 6 pi over 3. And then to get from 4 pi over 3 to 10 pi over 3, I need to add 6 pi over 3 again. So in general, our front term would look like, so I'm trying to come up with a general term for intervals of increase. So the first term will be negative 2 pi over 3 plus 6n pi over 3. So that's kind of the front term, if you will. Okay, and then the back, or the second term, so the kind of upper limit on each thing, are also different by 6 pi over 3, right? So to get from 2 pi over 3 to 8 pi over 3, add 6 pi over 3. And similarly, to get from 8 pi to 14 pi over 3, we need to add 6 pi over 3 as well. Okay, so that we could do as 2 pi over 3 plus 6n pi over 3. So ultimately, if we kind of simplify that a little bit, the intervals of increase in general will be, you can show this, 2 pi over 3, 3n minus 1, and the upper limits on each of those will be 2 pi over 3, 3n plus 1. Okay, so those are all the intervals of increase. So a bit of work, especially when you're trying to come up with an expression for things in general. Okay, all right, similar procedure for the intervals of decrease. Maybe I'll leave it to you to prove that the intervals of decrease are 2 pi over 3, 3n plus 1, to 2 pi over 3, 3n plus 2. Okay, so just follow similar procedure, right? Make a list like I did here, except do that with the intervals of decrease, and please show that's the case. Okay, you can, if you like, graph this. Obviously, might help to get Desmos going on your computer at home. I did that. Get out of the way. Here we go. So here's the graph. Okay, and then you can test out your rules with n. So try like n equals 1 or n equals 2, and you should be able to reproduce these intervals of decrease. So we're decreasing from there to there, from there to there, and so on. And it happens in a very predictable way. Okay, so that's it for that one. I'll also give you a little bit of a hint for example number 5. Okay, so example number 5, I'll just maybe save some time in this video. I don't want it to go for like 90 minutes or whatever, so maybe just have a look at what I've done so far. Okay, I've given you G prime. Okay, there will be some interesting boundaries where G prime doesn't exist. Okay, so there might be a very large interval where G prime doesn't exist, and some others where it's positive and negative. Okay, so set up like we did in the previous questions. Maybe set up your two terms. Okay, so you can do all your terms x plus 2 squared rooted, and x minus 2 squared. Okay, identify important boundaries. Maybe I'll just give them to you. -2 and -2/3. And I'll leave it to you to figure out whether those are increasing or decreasing. One thing I'll maybe add, x minus 2 will be increasing, or sorry, positive for any value you put in for x, right? Because we're squaring it, it's always going to be positive. Okay? This one is a little bit different. The other ones though, like here and here, 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 and here, those are either going to be positive or negative. Okay, these aren't negatives necessarily. Okay, I just put those in for so you can see what remains. All right, so if you could maybe just send me a photo of your work when that assignment is due. Just want to see an attempt. Okay, don't stress too much. Just make an honest attempt and send me something, and I'll just check it for completion. Okay, all right. So on to today's lesson. Sorry, this is coming up a little bit later than I would have liked. Kind of splitting my time between tech support and making stuff for you guys, so you know, hopefully I'll be able to get ahead of it a little bit more starting on Monday. Okay, ideally I'd like to have these ready for you for the day before, so you can get into EDSB and start right away if you want to do calculus first thing in the morning. Okay, all right, so we're doing maximum and minimum values today. Looking at this function f of x here, the function has an absolute maximum, so where is it the highest? It's right there. So the value of x there is 10, and the value of y at that point, so its height kind of is 8. And we have an absolute minimum down here when x is 2. And the value of y at that point is 0. Okay. In general, a function f has an absolute maximum at c, so some x equals c. If the f at c is greater than f of x for all x in the domain of f. So basically what that's saying is you found some y value that's the biggest. Okay, it's bigger than all the other y values of the domain of the function. So that's basically telling you that, right? So if that's the case, then f at c is called the maximum, absolute maximum value of f. Okay, and a function f has an absolute minimum at c if f at c is less than f of x for all x in the domain of f. So basically what we're saying there is that's the smallest y value that we've identified. It's smaller than all the other y values on the function. Okay, and the number f at c is called the absolute minimum value. Absolute minimum value of f. Okay, the extreme values of f are the absolute maximum and absolute minimum values of f. Okay, we have local maximum and minimum values to consider as well. Okay, so looking at the same function, the function f has a local maximum when x is equal to 4, so there's a peak, and x is equal to 10. there's another peak. So x equal 4 and x equal 10. The local maximum values of f are respectively, so we have 4, 5 and 10, 8. Okay, and the function has a local relative or relative minimum at x equals 7, so that we have a little bit of a trough there when x is 7, and the local minimum value there is 3, so that's the corresponding y value. Okay, in general, a function f has a local or relative maximum at c if f at c is greater than f of x in the neighborhood. Okay, so we're looking just on both sides of c. So for example, we have a local maximum here, just comparing it within that local neighborhood. It's the biggest in that area, so it's a local maximum. Okay, same thing over here. Just looking at the values of f in the vicinity of that peak. Okay, it's the biggest as well. Right? And a function f has a local minimum at c if f when x is equal to c is less than all the other y values when x is close to c. Again, on both sides. So that's a trough. If you look in the immediate vicinity of that trough, it's the smallest, so we call it a local or relative minimum of the function. Okay. You could probably speed ahead with these if you want. So by all means, if you want to skip ahead and check that you got this right, maybe try this out on your own, and I'll just work through it at my own kind of speed. Okay, so for this one, the function g does not have an absolute maximum, because it'll just go up forever that way and that way. Okay, it'll just keep going till infinity. We do, however, have an absolute minimum here, right? That's the smallest height, if you like, when x is -3. And the corresponding y value is -15. Okay. We also have a local maximum here when x is 1, and the local maximum y value is 10. Okay. We have local minimum twice, so one here and one there. So when x is -3 and 3, and the corresponding y values are -15 and 5. Okay. So that's definitely an absolute minimum, but if we're just narrowing our consideration to the neighborhood of that point, you could also call it a local minimum. Okay, so I guess ultimately, if we want to be most efficient, we'll just call it the absolute minimum, but it wouldn't necessarily be that incorrect if we call it a local minimum as well. Okay, this one is just a local minimum. It would be incorrect to call this one a absolute minimum, because it isn't. All right. Okay. Complete the following for h of x shown to the right, so that carries on to the next page. For if you're following along on your paper. Okay, h of x we have an absolute maximum when x is negative 1. And corresponding y value is 6. Okay, we also have an absolute minimum for this function here, and that happens when x is negative 4. And the absolute minimum value, so the corresponding y value is negative 4 as well. Okay, we have a local maxima here and here. So at negative 1 and 4, I guess that first one's kind of redundant because we already did, but all right. Okay, corresponding y values are 6 and 3. We have also a local minimum here when x is 1, and the corresponding y value is 2. Okay, onward. If we don't know what the graph of the function looks like, how do we find local max and mins? So just looking at our graph here, what values of x does it have a local max? Okay, we have a peak there, we get a peak there, we get a peak there. So when x is a, c, and e. A, c, e. Okay, what is true of the derivative at these values of x? So the slope in that, at that precise spot, is either 0, as it is in this case, okay, because we're going from a positive slope to a negative slope in each of these cases. And if we're going to transition from a positive to a negative slope, we need to hit 0 at that point where the peak happens. Okay. The other possibility, so for this one, because we have a kink or like a corner, the derivative doesn't exist. So it's either 0 or the derivative does not exist. Okay, next, what values of x do we have a local minimum? We got one there, and we got one there. So at x is equal to b and x is equal to d. Okay, and what's true of the derivative at those spots? So in this situation, derivative is 0, or again, because we have a kink here, derivative wouldn't exist. Okay, so that brings us to Fermat's theorem. If a function has a local max or min, then either the derivative at that point is 0, or the derivative at that point does not exist. Okay, which you can see in that diagram there. Okay, note the converse is not necessarily true. So looking at a function like x cubed, the derivative is 3x squared, and it equals 0 when x is 0. So, but the thing is, if we graph x cubed, it looks something like that. Okay, so right here at the origin is 0, but it's not a max or a min, right? So you can usually use your graphing calculator to verify that. So sometimes it's a point of inflection. That's what that's called. It goes from curve down to curve up. Okay, but we have something to work with now. Okay, so interesting points happen when the derivative is 0 or it doesn't exist. Okay, so we'll try a few examples. We got a function y there. Take the derivative, we got 3x squared plus 12x plus 9. Interested in when the derivative is 0, because we're probably going to get a max or min in those situations. We can factor out a 3, so we get that. And we can factor that further, so we get 3 x plus 3 x plus 1. So we're interested in when that's equal to 0, so that happens when x equals minus 3. And this thing is equal to 0 when x is minus 1. So the critical values, or critical numbers in this function are at -3 and -1. And you can go ahead and graph that if you like and see what's happening in the neighborhood. But there you go. Okay. Next one, y equals absolute value of x. So it's looking like -x from -infinity to 0, and it looks like positive x from 0 to infinity. So if we take the derivative of each of those, it's -1 on that interval, and it's +1 on this interval. Okay, because we have like a kink, the derivative doesn't exist when x equal 1. Sorry, x equals 0. So it's negative derivative to the left, so it's a -1 slope to the left of 0, and it's a +1 slope to the right of 0. Right, so it would look like that, and derivative just doesn't exist at when x is equal to 0. So the critical number for this one, x equals 0. Okay, last one. You may find it helpful to write it like that. So that's y. Derivative then will be 1/2 x to the -1/2. Or if you prefer, 1/2 root x. Okay, it'll be interesting for us when the derivative is 0. Okay, so that, when's that going to happen? Well, maybe first let's look at this thing. So looking under the root symbol, that thing can't be 0, because otherwise we'll divide by 0, which would be an issue. So we need x not equal to 0. Okay, the other thing, if we have x being less than or equal to 0, that would be an issue as well. So x needs to be greater than or equal to 0. So 0 is kind of the interesting spot for this. Critical value when x is equal to 0. Okay. And you can graph that as well if you like. The graph of the square root of x would be like that. So positive square root of x would look like that. And we bump into issues at that point. Okay, next. We have the same function that we just did in example above, part A. We already have the derivative, which is 3x plus 3, x plus 1. Interested in areas where the derivative is 0. I guess we've done this already, but we go. So critical values will be -3 and -1. All right. We are looking to determine local max and min values there. I'm going to kind of do a little bit of a similar procedure to what we did yesterday, or last class. Set that up. Okay, we got two factors, x plus 3 and x plus 1. And we'll just look at the boundaries there. Okay, for x plus 3 to the left of -3, that term's going to be negative. To the right, so in between -3 and -1, that term is going to be positive. And to the right, so any x being greater than -1, that term will be positive still. Okay, next one, x plus 1. If I chose x equal -4, for example, that term's going to be negative. Okay, between -3 and -1, so for example, if I picked x equal -2, again, that term's going to be negative. And then to the right of +1, or sorry, -1, it's going to be positive. So if I chose x equals 0, for example, that would be positive. Okay. Because the derivative is the product of this, and there's no other signs to consider, the derivative will be positive there, right? Because we're doing negative times negative. It will be, so the derivative will be negative here. So that means the slope's going to be negative, right? Because we're doing positive times negative. Just do those, okay? And then doing positive times positive, that's going to give us a derivative on that interval that's positive. Okay, so ultimately, the function will be increasing as we go from -infinity to -3. It'll be decreasing from -3 to -1, and then it'll be increasing again from -1 and beyond. Okay, if we're going from increasing to decreasing, there's going to be a local max potentially there. And if we're going from decreasing to increasing, I'd expect there to be a local min at that point, at that particular point. And at that particular point, we would expect a local max. Okay, we need to figure out now what the coordinates of those points are. So what's the value of the function when x is -3, and what's the value of the function when x is -1? So y, when x equals -3, you can just plug in everywhere you see an x, you put a -3, so -3 cubed plus 6, -3 squared plus 9, -3 plus 2. That turns out to be 2. And y when x equals -1. Okay, same procedure, just sub in -1 in for y. You get -2 there. Okay, so we'll have a local max at -3, 2. And we'll have a local min at -1, -2. Okay, and we need to do a little sketch of this. Okay, notice this function is cubic. The leading term is positive, so it's going to start in quadrant 3 and end in quadrant 1. It's going to go through the y-axis when y equals 2, so it's going to be like kind of through there. We've got a local max, negative 3, 2. And we'll have a local min at negative 1, negative 2. Okay, and beyond that, I guess you could figure out what these, what the x-intercepts are going to be, but we're just sketching it. Okay, it'll look kind of something like that. And you can graph the function to confirm that that's roughly what it looks like. Okay. Next, we're restricting our attention to, so same function, determine the absolute max and min values of the function on this interval. So we're just kind of restricting our attention to between like negative 5 and 0. Okay. So in addition to the local max and local min identification, which we've already done, so those are important ones to consider. We're also going to look at the end behavior on the interval. So the function y when x equals negative 5, you can sub in negative 5 for all these x's, right? And simple enough, you get negative 18 out of that. And we can look at the function value when x is 0, so that's the other endpoint. That's going to be 2. So we would have one coordinate to consider, negative 5, negative 18, and 0, 2. Okay, 0, 2 matches that other maxima. So 0, 2 would happen there, and then we have 3, 2 as well. So on this interval, so on the interval, negative 5, 0, we have local maxima at negative 3, 2 and 0, 2. And we have an absolute minima at negative 5, negative 18, right? That's the lowest y value, right? The other local min doesn't even compare. Like it's nowhere near as low as the endpoint there. Okay, all right. So last on that page, procedure for finding absolute max and min values. Okay, you can have a read through that. Example number 5, fortunately it looks like it got printed at the bottom of that page, but you got a little bit of room to work on the next page, so you can just flip that, I guess. So we're going to do find the local absolute max and min values of this. If we're restricting our attention to an interval, we should probably figure out the end behavior, and we should do our normal procedure, take the derivative of the function, figure out when it's equal to 0, and see if there's any local max or mins happening. Okay, so it might be helpful for you to take the derivative if you write the function 2/3. Write the function like this. So just distribute that into each. Okay, and then the next term would be 2/3 plus 3/3 would be 5/3. So x to the 5/3. Okay, and now take the derivative. So that would be 10/3. X to the minus 1/3. plus 5/3 x to the 2/3. Okay, we can simplify this, maybe factor out a 5/3 x to the minus 3, minus 1/3 rather. I think that factor looks a little bit more obvious when you consider this form of the step above, so the 5/3 x to the 2/3. So we're just looking to factor this out so we can get rid of any things in the denominator, right? So hopefully that's somewhat helpful. So we're trying to get rid of the denominator, I guess, when we have things in brackets. Okay, if I were to distribute this thing back in, this first term would need to be a 2, and this second term would need to be just a plain old x, right? So if we considered x to the 3/3, which is the same as just x, 3/3 minus 1/3 gives us 2/3, which is what we need. Okay, so that looks pretty nice in the brackets there, and lets us analyze the derivative a little bit easier, I think. Okay, alright, so interesting points will be when the derivative is 0, right? That'll happen when x is 0 from that term, right? Well, I guess that thing's staying there. And from this, when x is -2. Okay, so x to the minus 3, right, would be, or sorry, x to the minus 1/3 would look like that. Okay, we can't have x being 0 because then we're dividing by 0, and that's a problem, so I guess I should have written that. X is not 0. Okay, those are our critical values. So we're looking to investigate what's happening to the derivative around those boundaries. So at -2 and 0. Okay. One of the factors, right, we have 1/cube root x, and the other one is 2 plus x. Okay, 1/cube root x is negative on that interval. It's negative on that interval as well, and it's positive to the right of 0. Okay, 2 plus x is going to be negative on that interval. It's going to be positive on that interval, and positive on that interval. Okay, because y prime is a product of this and that, we're looking at a positive derivative on that interval, a negative on that interval, and a positive on that interval. So that basically means slope is positive, slope is negative, slope is positive. Okay? What that means for the function itself, it's increasing, then decreasing, then increasing again. So we could have a max there. We could have a min there, very likely. Okay, so altogether, at the end behavior, so when x is -5 and x equals 0, you can just plug in -5 wherever you see an x in the function. That turns out to be 0, so that's going to be a coordinate -5, 0. Okay, the next one would be, I try to do it to scale as best I can. Oh, hang on. The other endpoint is 1. Okay, and then 0 was another interesting point, and then 2. Okay, the function value when x is -2. Okay, so just sub in a -2 wherever you see x. That turns out to be 3 cube root 4. Okay, so -2. What is that? That's not a 3. 3 cube root 4. Okay, which is approximately like 4.76. Okay, and then function value when x is 0 turns out to be 0. So we have 0, 0 there. And the function value when x is 1 is 6. So we have 1, 6. Alright. So now we can go through and look at all our y values, right? 1 should hopefully stick out to be the largest. So this one. That's an absolute max. Another one should look hopefully to be the smallest. Looks like a tie between this one and this one. So we have a local min here and another local min here. Okay, and then looking at -2. Right, so -2 was there. It's going from increasing to decreasing. That should be a local max there. So this is local max. Okay, good. All right, please try these ones out. So example 6 and example 7. Do your best. Okay, just try it out. I don't think I'll check these. I think maybe just focus on doing your derivatives assignment, which is due shortly, right? Monday at midnight. So maybe just focus your energy on that, and please try example 6 and 7 if you get a chance. Okay, that's it. Have a good day. Bye.